presenting the jury. This is the order that the questioning will be done also. So there are two rapporteurs, reviewers for the thesis. Neil Sandham from the University of Southampton and Lutz Leschak from École Polytechnique. And then followed by the examiners, who will be Peter Jordan from Peprim in Poitiers, then Samir Benedine from Onera, Grégoire Font from Airbus in Toulouse, and myself, Tarameh Sayadi from CNAM in Paris, and of course the two advisors, directors of the thesis, Jean-Christophe and Nicolas Alphax. So Alessandro, you have about 45 minutes, and then after that we'll continue with the questions.
Okay, thank you. So hello everyone, thank you for the introduction. I thank the jury to be here, that they accepted to be the reviewer and present today at my event. I'm Alessandro Franchini, as they presented, and my work is done in collaboration with the Mambo project, which is a project made in collaboration with Airbus and the GAC. And today I want to present you my work about global stability analysis with automatic differentiation with an application on turbulent jets. So okay. So the goal of this thesis is to try to use to study the big structure, the turbulent structure that appears in supersonic flow and in compressible flows. The idea is to use stability analysis to provide some information about the dynamics of flow. The problem is that in turbulent flows, there is a difficulty where since the regimes sometimes always have multiple scales that interact, and we want to find a way to model the dynamics as a perturbation over a stationary field. So in literature, there are mainly two ways within the global stability analysis framework to extract coherent dynamics of turbulent flows. There is the approach of mean flow, which means that we use high fidelity simulation data like data from LES or DNS, or data from experiments. And then we perform global stability analysis over the Navier-Stokes equations. Or we can use some low fidelity modeling, such as URANS, in which the Navier-Stokes model is closed and the turbulent fluctuation are modeled via the mean flow terms. So in our thesis, we will be presenting this the second approach. But URANS, so the unstationary URANS equations, are well posed when there is a clear separation of turbulent scales. And in this case, it has been shown by, for example, the work by Crouch in 2007 and 2009 to work well to predict the global instability features of a turbulent flow. So now what we want is to perform global stability analysis over URANS fixed point, but to do that, we need the linearized equation for URANS. So again, usually the main approach is that of first we differentiate the equations. So we take the Navier-Stokes equation with the URANS modeling, and we calculate analytically the equations. But this could be tedious, and for each boundary condition, if you change the geometry, if you change the turbulence model, we need to redo the calculation, and sometimes this could be very time expensive. So there's another approach that we will pursue in this thesis, which is called first we discretize the equation. So first we generate the code that is solving the equation, and then we'll differentiate the nonlinear code, and we will get a linear source code. In order to do that, we will use an approach which is automatic differentiation, in which a program generates a new solver that is the linearized one. So the objective of this thesis has been to try to develop a solver to perform three-dimensional stability analysis within this framework, using automatic differentiation to derive the linear equation, and then we want to apply these methods to compressible turbulent flows. So this is the timeline of the presentation. First, we will talk about the mathematical framework that we will present. Then we will take a deep dive into the numerical framework and the solver that we want to use. And third, we will do we'll see at an application, so a real case of switching jets, and we will look through the fixed point calculation, how we perform global stability analysis, and then we'll use this data to analyze the feedback loop which is inside the switching jet, and then at the end we will present conclusion and perspectives. So our mathematical framework is that of the Urans modeling. In here we wrote it as where F is the Navier-Stokes operator with a Boussinesq closure, Q is a state vector, and we separated the turbulence variable vector so that we have a model which is the partial derivative of phi depends on a turbulence model operator, which depends on the state variable Q, which for us will be velocity, momentum, and total energy. And the Boussinesq hypothesis, we can formalize it by saying that the mean of the turbulence fluctuations, the Reynolds stress tensor, is actually modeled by an operator that depends on the turbulent eddy viscosity, the state variable, and the turbulent variable vector. And then, in order to provide a conversion for the turbulent variable vector and the eddy viscosity, we will use another operator M, which, for example, if we take the K omega model, the phi vector will be the turbulent kinetic energy and the dissipation rate, and mu T will be, for example, proportional to the ratio between the turbulent kinetic energy and omega. So now, as is always done in stability analysis, we will take our state vector with turbulence variable, and we will say that it's composed of a fixed point vector plus a small perturbation, infinitesimal perturbation, where the fixed point solution is a solution of the stationary equation here, so where the derivatives on p equal to 0. If we develop the first order Taylor expansion around this fixed point solution, we get the linearized Urans equations, in which here I separate the Jacobian terms, in which, for example, the derivative of f over q is the first block of the Jacobian matrix, in which there's the derivative of q, then there is the derivative of the turbulence variable. And so here now we solve over the perturbed vector. So now we can, from this linearized equation, we can extract the Jacobian of this system, which is, again, the matrix made by these block matrices. And we know that in stability analysis, the dynamics of a small perturbation over this fixed point solution is given by the eigenvalues and eigenvectors of this Jacobian matrix J. So now the question is, how can we actually obtain J in real cases? And if J is large, how can we approximate it? So for the first question, we will use automatic differentiation in order to approximate J. And then with time-stepper methods, we will approximate the effect of J over a vector in order to prevent the cases with J is very memory expensive. So now I will present the numerical framework. So first, I will talk about the automatic differentiation code, which is stop and add, which is a tool that computes direct or adjoint derivatives. For example, it works by giving a routine to differentiate. You select the dependent and independent variables, and this will generate the differentiated code. So here, for example, if we have a variable which is defined as the square root of another variable, in here, the differentiated code, we will have the analytical derivative of this first variable. The other part of our framework is the nonlinear solver, which is called Dynami, and it's been developed by Nicolas Alferez, which is my co-director, and is a multi-language Python, Fortran, and C framework that is able to solve problems of this form. So the partial derivative of Q over time equal to a right-hand side which depends on Q. The Dynami is a generative framework. It has a time discretization, which is a Runge-Kutta of third order, as described in the Shu and Osher paper of 1989. As a spatial discretization, we can choose an arbitrary order centered final difference, or arbitrary order final difference, actually. And for the dissipative schemes, we can use filtering, or in the case of compressible flows, we can also have a shock capturing scheme as described in the Jameson paper, and with higher order generalization as described from the paper by Jacovelli. It works on structured grid, and the parallel communication are managed by the open source code Cassiopeia, which is developed at Onera and it has been described in the paper by Benoit in 2015. So to give an example of how this framework works, for example, if we take a Burger's equation, which is an example of an equation written as dq on dt equals RHS of q, we get a mathematical expression. We write the symbolic Python of this mathematical expression, and we have a Fortran generated scheme. Then we get this Fortran generated scheme, we use tap and add, and we will get the Fortran differentiated code. So here, for example, we can see that the square term in the Burgers has become the differential of this variable, so which is 2q times qt. Now, what we want is to construct a linear module of dynamique, but we also want to inherit the first peculiarity of dynamique. So we want to maintain its parallelization, its multi-block structure, and its performance. So if, for example, dynamique solves the problem of dq dt equal RHSQ, we want a framework that is able to solve dq prime in dt equal the differential of RHS, of which depends on q prime, actually, and q0, the fixed point solution. So, for example, the way it works in practice is that we get the nonlinear dynamique code, and we have a dynamique template which has the declaration of the variables. Then with tap and add, we take this nonlinear dynamique code and we get the tap and add code which has a different structure than the original code. Then we extract the part of the tap and add code and we insert it inside the dynamique template, so that in the end we get a fully functioning linearized code which has the same structure of dynamique. A thing that we have to modify is the memory structure, because dynamique in practice works by defining a state field, and for example you can define auxiliary fields in order to better write the equation in symbolic form. And the nonlinear fields are which represents the nonlinear fields Q, and it's a contiguous memory in which each data is contiguous from one another. And actually what we can do easily is that we can use the same memory structure that is being used in the nonlinear fields Q for our perturbation field, since they are automatically given. And then automatically we will extend this memory to take place for the fixed point fields, which will be the fixed point fields of the state variable Q and also of the auxiliary fields that depend on the state variable. So now that the linear solver is ready, we want to use this linear solver to calculate the eigenvalues and eigenvectors of the Jacobian matrix that we showed before. Now, to do that, we chose the time stepper method, because for some very big cases, very data expensive cases, the memory footprint of this Jacobian matrix can be very high. And so the time stepper method is a method that is able to never assemble the Jacobian matrix. And so we just use the application of this matrix with a vector. So the way it works is that if we reformulate the discrete time framework of the linear solution through its discretized form, M is the exponential propagator. Here, Q prime Qk represents the Q prime at time at discretized time k, and k plus 1 is the discretized time k plus 1, which are spaced by a sampling period tau. If we now, with the linearized code, we actually, each snapshot in time of the linearized code is actually an application of this exponential propagator over the perturbed field Q prime K. So we select these snapshots, and using some iterative methods of linear algebra, we get the spectrum of the exponential propagator. Now it's easy to recall the spectrum of the Jacobian, since it's just the logarithm divided by the sampling period tau. In order to find the fixed point solution, we have, say, a similar strategy. So we employ the Newton-Krylov method, in which phi tau is the discretized nonlinear solver, which advances in time a time tau. And so a fixed point solution is a solution that satisfies this equation here. And then, in order to perform the Newton iteration, so at each time step, we will have a residual vector made from the difference of these two terms. And then we will have to, as a classical Newton algorithm, we will have to invert this matrix here. So we have to solve this linear problem. And then we can use the linear solution of this linear problem in order to update this the solution to converge to the fixed point. And here the time stepper method will be used inside this linear system that is solved at each Newton iteration. And to solve that, we will use a time stepper GMRS method. So to recall the whole solver and the whole numerical framework, we can start from an equation written in symbolic form. Then with dynamic, we will get the nonlinear source code. Then we will take this nonlinear source code and we will inject it inside Tapenade, and we will get the linear source code. Now, by combining the two nonlinear source code and linear source code and using a time step and Newton-Krylov method, we get the base flow. And then using the base flow inside the linear source code, we will use a Krylov-Schur algorithm in order to get the spectrum, so the eigenvalues and eigenvectors of our problem. The linear algebra solver that we used are the one given by PET-C and SLEP-C, which are some high-performance parallelized solvers that can compute the linear algebra problem. This linear framework has been validated in different configurations. First, we used a linear isotropic vortex advection problem in order to validate the linearized Navier-Stokes equation in curvilinear mesh. Then we validated with the density spot shock interaction to validate the differentiation of the shock capturing scheme. In order to validate the global stability framework, we did a classical case of a laminar cylinder. And then actually the Uran's validation has been done by another PhD student, which is Donato Variale from our lab, which has performed the Buffet case. And so he found the density. For example, here there is a comparison on the density component of the unstable mode for the Buffet case, which is an instationarity of the shock, which appears at in an airfoil case. So now that we presented the numerical framework, we will take a dive into the application of this thesis, which has been one of the application of this thesis, which has been the screeching jets. So screeching jets are the screech in supersonic jets is a kind of noise that appears in supersonic underexpanded jets, which are jets in which the pressure at the inlet is higher than the free stream pressure, and so there's a shock cell structure that appears in the jet outside the nozzle, and the instationarity of these shocks can generate some acoustic noise that has strong upstream reactivity. So if we look at for example, of an acoustic spectrum of a supersonic jet, here you can see that there are three components that appears in underexpanded jet. There's the turbulent mixing noise that are low frequency coming from the hydrodynamic instability of the jet. There's the broadband shock noise, which is a kind of broadband noise that appears when the downstream propagating waves interacts with the shock cell structures. And then the one that we want to study is the screech tone here, which is this precise peak tonal noise that appears in between these two broadband noises. And this kind of noise can cause sonic fatigue and can damage aircraft component when it's too loud. As the screech has been always, since the first work by Powell in 1952, it has been studied as an acoustic feedback loop in which, for example, a downstream propagating waves is excited, the Kelvin-Helmholtz instability is excited at the nozzle lip. Then it interacts with the shock cell structure and generates acoustic noise. Then there is an upstream mechanism that propagates this energy upstream and then re-excites the nozzle at re-excites the downstream propagating waves at the nozzle lip, and so this closes the loop, and we have a feedback loop that is resonating. And here in this image, we can see the acoustic waves that are propagating upstream, typical of screech. Our objective in this work is to try to describe the feedback loop using global stability analysis. The numerical configuration that we want to study is the one of a convergent nozzle. Here, this convergent nozzle is immersed into a free stream of MAC, of ambient MAC of 0.01. We have some stagnation quantities that are accelerated into convergent nozzle, and we get some temperature, pressure, and MAC at the exit of the nozzle. We will model the nozzle lip thickness, which will be HL. D is the diameter of the nozzle, and the Reynolds number is 2 million, which is so that we are in a fully turbulent case, and we will simulate a cold jet, such that the temperature ratio is equal to 1. The main parameter that describes this mechanism is the jet pressure ratio. So it's the pressure between the nozzle exit and the free stream pressure, and we will simulate over these values here. And another quantity that is equivalent to this JPR is the MJ, which is the fully expanded jet Mach number, which is equivalent to the Mach number that we need in a convergent divergent nozzle in order to get a perfectly expanded jet. Our numerical configuration in here, we can see the mesh that we used. We have a multi-block structured 3D mesh, which has approximately 6 million points, in which, again, the parallel communication has been managed by Cassiopeia. If we get a cut of this mesh, we can see that there is a physical domain which is highlighted in blue that goes from 10 diameters upstream and 45 diameters downstream, and 10 diameters in the radial direction. Outside this physical domain, there is a sponge layer that is used in order to reduce the oscillation coming from the interaction of the acoustic noise with the boundary. And then in the boundary, we also impose characteristic non-reflective boundary condition to further reduce this effect. If we look more deeply at the mesh, here the different color represents the different blocks. So the boundary condition in the nozzle is the one of adiabatic nose lip. Here we have the inflow. We don't model the inside of the nozzle since it has been shown in literature that it is not very important in order to select the frequency of switch, and it's not important in the actual feedback loop. So we just put a supersonic inflow of Mach equal 1 at the x equals 0 here. To treat the singularity in the mesh, that it will appear when you rotate a three-dimensional mesh, we will use an OH topology that is shown in here. So D is the diameter and HL is the nozzle lip thickness. The solver parameters that we used are a central final difference of 6th order. We used a Jameson shock capturing scheme of 5th order, as in Sciacovelli and others of 2001. And we will use a K-log SST model with compressibility correction. And we use the log omega model in order to reduce the effect of the big gradients that can appear near the nozzle, near the boundary layer that could generate some numerical oscillations. Then we linearized with automatic differentiation this K-log omega SST model, and at this point we asked the question if is correct to differentiate automatically a model which is non-differentiable, and we found that there were some work in which, with a particular definition of correctness, we can say that if we have a function that is defined analytically, defined inside analytical partition, since the automatic differentiation is actually a differentiation by parts, this is correct, and we can we just are not we can continue to use this approach. For the global stability analysis, then we perform global stability analysis, and we perturbed this state vector, which is the classical component of compressible fluids, plus the turbulent variables. Now, first we calculated the fixed point solution. Here we see the density components of two cases, one with the lower under expansion and the other with the higher under expansion. You can see that with increasing level of under expansion, the main difference is that the shock cell structure, so all these shocks are further apart, and are you can see that also the jet core is larger when at higher level of under expansion. If we have a look at the velocity diversion, we can see, for example, here it's the case of mj equal 1.45, so the higher under expansion case. We see that by looking at the velocity diversion, we can see that first we have an expansion. This expansion rebounds in the boundary layer and generates compression waves that here coalesce into oblique shocks, and then this structure repeats. And if we look at the angle of these oblique shocks, calculating over the incident flow, we get a 57-degree angle, which is the one that is predicted by the literature of oblique shocks. The dashed green solution represents the sonic line. So inside the jet, we have a supersonic flow, and outside we have a subsonic flow. Now, in order to validate the fixed point, we focused on the pressure center line, which is one that can provide us the correct shock spacing and the correct shock strength, which are the most important characteristics in screech. And you can see here that we get very close results for the nearer nozzle case with the compared from experiments. And we compared also from an older Urans calculation made by Shen and Tam in 2000. And you can see that we follow the main structures of the experimental flows. So for each case, we validate by looking at the shock cell spacing. And here we can see that the blue is the one calculated in our simulation. So where LS represents the shock cell spacing, and we can see that we follow the curves from experimental data coming from Agent Mitchell and two different works. So now that we have the fixed point solution, we can do global stability analysis over these fixed point solutions. First, before going into that, we want to first introduce a behavior that appears in screech, in which there are two different kinds of modes that are actually capable of generating this acoustic instability. One is an axisymmetric mode that has azimuthal number m equal 1. So it's you can see here it's a toroidal motion that moves the shocks. And then there is another one that can appear at different under expansion levels, and is a flapping helical mode which has azimuthal number of m equals plus minus 1. And here we can see that the pattern of movement now comes in this direction. So if we take a look at experimental data of the wavelength of these screech tones, you can see that we can separate these two in two groups. There is the A1 modes and A2 modes, which are here. This is the wavelength, and this is the level of under expansion. These are the m equals 0 axisymmetric mode. And then there is the B and C modes, that are these here, that has an azimuthal number of m equals plus minus 1. Here we can see that the behavior, we have a behavior in which for some level of under expansion, we can experience two different modes. And there is a jump or a switch sometimes from mode to mode that we will explore later. Now, before looking at the global stability analysis, we want to first introduce what kind of spectra we can see in model analysis. For example, here one type of spectra is the one that represents a self-sustained motion, like that of a stable or unstable laminar cylinder. So here we can see that in these cases we have a mode that is separated from all the branches, and it has a precise frequency, which is the one of the self-sustained motion. This here, for example, is the mode of the cylinder flow. Then we can find also some discrete branches of acoustic modes that are separated and have a different, and are here shown in this particular structure, and is the one, for example, in the cases of when there is a jet that impacts an oblique plate. Another case is the one if you try to apply model analysis over convective instabilities, then you get a temporal, since the flow is not self-sustained, you will get branches of continuous convective modes which are stable, and for example here is the case of a boundary layer problem. So first we start from the lowest under expansion, and we see the spectrum for the MJ equal 1.1. You can see that we see the branches of convective mode, and here we can see an unstable mode that, if we look at its structure, we can see that its frequency or its wavelength lies near the experimental one, and the shape is actually an axisymmetric mode of azimuthal number m equals 0. And if we look at its dynamics in time, we can see that we see the downstream propagating wave, which is a Kelvin-Helmholtz wave, and an acoustic wave that propagates upstream, typical of screech. And here, if we take a cut at x equal minus 0.5, we can see the shape of the acoustic wave, which is a torus, and so it's a mode of m equals 0, so azimuthal number m equals 0. Now, if we look at the eigenvalues of the case mj equal 1.2, here we can see that the modes are stable, but we can select some modes that are more detached from the branches of convective modes, and still, even if they are stable, so it means that the nonlinear analysis was stationary in time, we can still analyze its modal structure. And if we look at the modes, the first one is an axisymmetrical mode again, which actually correctly predict the frequency of this mode. And again, we can see that it has a similar structure of an axisymmetrical mode, so downstream propagating wave and upstream propagating wave. Here we can see also a kind of a Mach radiation that propagates downstream. Then, if we take the other mode, we have a mode B. So now, actually, we have a mode that has a different symmetry, which is the symmetry of azimuthal number m equals plus or minus 1. We correctly capture the frequency. And again, if we take a look at the structure, now we have a different, we have an antisymmetrical movement for the velocity component, the streamwise velocity component, sorry. And we can again see the upstream propagating wave, downstream propagating wave. And here in the cut, there is this helical or flapping motion that is clearly visible. Again, we look at another spectrum, and now we refine another nonlinear unstable mode for a Mach J equal 1.25. And this mode now, if we look at the experimental data, again, correctly capture the frequency. It has azimuthal mode number of equal plus or minus 1. And again, it has the correct features of screech. If we continue analyzing these modes, now we get the most under expansion case that we studied, which is the MJ equal 1.45. Here now, again, we find all stable modes. We try to select the most detached one, which seems the most reasonable to study, which are the least stable, and also are the most detached from the convective branch of modes. And again, we correctly capture the frequency. For example, here is the mode B, so that the one with the lower frequency, yes. And again, you can see the different structure here. We can see that by increasing the level of under expansion, also the modes are spreading far apart, since the jet is longer, and so this reflects also in the mode. here we get again the whole structure, and quickly we see the last one, which is the C mode here. We correctly capture the frequency, and again it has the typical structure of a flapping mode. Now that we have the characteristics of the modes that we found, we want to try to see if we can get some information about the feedback loop within these modes. And if we recall the feedback loop, as of today, the modern understanding of this resonance loop is that the downstream propagating wave is a Kelvin-Helmholtz wave that is a classical shear layer instability. Then there is sound generated by the interaction with this Kelvin-Helmholtz with the shock structure. At this point, there is an upstream propagating wave, the upstream wave that propagates, which is called K minus, and this K minus wave excites again in the nozzle lip, in the near nozzle lip region, and it closes the loop. So now, since the mode represents a resonance feature or a self-sustained feature, we want to see if we can extract the wave information from these modes. And so we use a fast Fourier transform in the spatial direction, in the x direction of the modes, in order to explore and separate its components in the velocity phase, in the spectral domain. In order to do that, first we have to talk about the composition of the shock cell structure, since it is important for the understanding of the interaction with the Kelvin-Helmholtz mode. For example, if we take the shock cell structure here of a fixed point solution, and we say that it can be seen as a sum of modes that have a different wave number in the x direction. And if we take now empirically, what we can do to extract this information is we can take the center pressure line, we can take the pressure components of the center line, and we can do the fast Fourier transform. And here we can see that we get different peaks that represent the wave numbers KS1, KS2, and etc. And here we compare this fast Fourier transform with ones coming from experimental data that are actually data from the paper by Hamilton Mitchell. And for example, here is the FFT of the center pressure line, and MJ equal 1.45. And we did this because in TAM, in the broadband shock cell shock noise theory, what TAM in 1982 did is that he said that there is an interaction between the Kelvin-Helmholtz downstream propagating wave and this shock cell structure written in this way. And if we take the first mode, so the higher mode of the shock cell structure KS1, and we take the product that arises from the convective term of the equations, this interaction can give rise to two wave numbers. One that is the sum from KS1 and K Kelvin-Helmholtz, and the one that is the difference between the two. And if KS1 is bigger than KH, the Kelvin-Helmholtz wave, then this K minus is negative, and so the velocity phase of this wave propagates upstream. In here, we model the Kelvin-Helmholtz as a simple monochromatic wave in the x direction. So the idea is that there is the Kelvin-Helmholtz wave that propagates downstream, and when it interacts with the shock cell structure, there is these two waves that are generated, the K plus and K minus, and this K minus is responsible to the closure mechanism of Stritch. So now what we can do is take the fast Fourier transform of the mode, for example, the one that has an unstable mode, which is the one that mostly represents the self-sustained property, and we do in the x direction the FFT of the in the spatial in x, and we compare in the radial direction with the experimental data, and we can see that there are the three structures that arises and that are in common, which are here it is the K minus. Here we plotted in red the KS1 wave number, and the acoustic wave number are in dashed white. Here we can see that the K minus is represented by this structure here. Then the Kelvin Helmholtz is the most amplified one, and it's in here, and it's very similar to the one coming from experiments. And then there is the K plus, which is the last one, which has this structure again. This is the fast Fourier transform made of the velocity, streamwise velocity component mode. We have the complex part, because the FFT is non-symmetric. So we take the whole complex mode, to be precise. And so what we can do is to extract, we can take, for example, this wave here, filter the other ones, and do an anti-transform. And so here we can see the K plus the Kelvin Helmholtz wave that propagates downstream. We compared it with experimental data from SPOD data, and we can see that the structure is very similar. If we look at the K minus wave, again, now the wave propagates upstream, which is because the phase velocity is negative. Here again, we see the similar structure by compared from experimental SPO data coming from Edgington and Mitchell paper. Now, the upstream K minus wave has been described as the upstream propagating mechanism responsible for the closure of Screech. This is part of a subsonic wave coming from the description of TAM. When you put a vortex sheet model and you calculate the solutions, you get supersonic, Kelvin Helmholtz wave, and subsonic waves. And in his paper, TAM showed that there is a range of frequency in which this is the velocity group, this is a dispersion relation phase graph of different modes, subsonic modes of this family of waves. And you can see that in here, there is a part that propagates upstream because it has negative phase velocity, negative group velocity. So the way it's described is that it propagates. This can be possible because there is the free stream is subsonic, and so the waves can still be attached from the jet and propagate upstream, but still can have a support in the supersonic part. So in here, for example, if you take the radial structure of this upstream propagating mode coming from the TAM paper, here there is the boundary of the jet. You can see that it has a support in the supersonic part, but the main thing to see is that it has also support in the subsonic part. And if we take a look at our mode and we compare it with the experiment from SPOD data, we take the radial structure of our K minus mode and mode from SPO data, experimental SPO data, we can see that we correctly capture, or at least in the supersonic part, the structure of this mode. And this upstream, let's say the discovery of this of the K minus as the upstream closure mechanism has been done in many papers, the one made by Peter Jordan and others, also in other cases of acoustic resonance like impinging jets and others. If we take a look now at the absolute value of this K minus spatial distribution, we can see that the maximum of this mode is between the fourth and fifth shock, which has also been the peak sound source in experiments from K and others. Here the dashed line represents the shock location. And another particularity of Screech is the mode staging. So again, if we take a look back at the spectrum, we can see that for some level of underexpansion, there is also a jump in frequency. And in some recent papers, this staging mechanism has been associated with the interaction, not always with the first KS1 peak of the fast Fourier transform of the pressure of the central line pressure, but also with the second one. And so, for example, what we did is we compared our KS1 and KS2 with the one coming from experimental data. And we can see that for the KS1, we have a good agreement. For the KS2, we have a good agreement for the case MJ equals 1.1 and MJ equals 1.44. For the other here in the middle is not that good. So we will try to see our data in the KS2, in these two cases. In these papers, the staging mechanism has been described with the KS1 being the interaction of the Kelvin-Helmholtz for the mode A1 and B, and the KS2 being the cause of interaction for the A2 and C modes. So what we did is we looked at our spectrum and we calculated the interaction of the Kelvin-Helmholtz minus the KS1 and Kelvin-Helmholtz minus the KS2, and we see which are the best agreement that we get for each mode. So here we actually have a better agreement with the KS1, which is the one that actually is responsible for this mechanism. For the case of the mode A1 at MJ equal 1.1, we have a look at mode B of MJ equal 1.44. We expect that this interaction, since it's a mode B, comes from the KS1. And again, it seems here is less clear, but it seems that the maximum is nearer the KS1 interaction. Here, these FFTs now are done, since the modes are flapping, are mode with the radial component of velocity. So the span-wise component of velocity to have this FFT distribution. And so here we can say that it's actually the interaction with the KS1. If we take now the mode C, here we actually see that now the interaction seems more near this KS2 peak, and it's actually the one that is experienced in experimental data. So to conclude, we developed a tool to perform global stability analysis in a generative framework using Dynami and Tapenade. We described some parts of the resonance mechanism of the screech in a fully 3D turbulent case. The computational cost that we employed in all our simulation is that of Uran's and Ran's simulations for the nonlinear and linear case. And we automate this method using automatic differentiation so that we can easily maybe change some parameters and models for the implementations. As a perspectives, the idea would be to try to study cases which has a similar acoustic resonance behavior. For example, in our work, we did a small test of a two-dimensional case of an installed jet case, in which, for example, for this configuration here, we have a subsonic jet that impacts a plate, and experimentally, it has been seen to show some acoustic tonal noise. And so we perform global stability analysis on that, which we see that we have these acoustic branches of mode, and if we take the first one, we get this structure which actually has some you can see the acoustic waves and some of the structures that can describe this. But it's still a small case, and it should be developed more with maybe a three-dimensional modelization in order to be better compared with experimental data. Then, as a perspective, these methods could be used also to study the sensitivity of both turbulence model of different parameters of different modelization. Here, for example, what we did is also start to a case of a 2D planar screech case. And we tested this case with two different turbulence models, a K omega SST model and a spiral Tamaras model. And you can see that the growth rate, here is the growth rate with respect to the most unstable mode with respect to the MJ, the fully expanded Mach number, can greatly vary with respect to the turbulent model. And here, for example, if we take the case in which the spiral Tamaras is stable and the K omega model is unstable, we can actually see that the turbulent antiviscosity of the spiral Tamaras is much higher in the near logical region. So maybe it has a very high dissipation that cuts and can dissipate too much the instability, and so preventing the self-sustained mechanism to be active. As other perspective, we can, in automatic differentiation, we could use the adjoint in order to calculate the linearized adjoint equation of the compressive Navier-Stokes equation with turbulence model. And with that, since we found many stable configuration, we could do resolvent analysis in order to study why these modes are stable, if they are really not, or if it's just a case of a problem of the turbulence modeling that is not able to correctly capture the growth rate of the instability. So thank you for your attention, and if you have questions, feel free.
Oh, it's coming.
Yeah, I imagine.
Don't worry. Thank you, Alessandro.